morning or good afternoon. My name is Professor Duke Orata. We are continuing with our thermodynamic lectures. Today we want to look at combined heat transfer processes. So what does that mean? When you talk about combination, it means that there are several components to something. So when you're talking about combined heat transfer, then it means that in that particular process, heat transfer process, we could have a combination of the various individual processes taking place. It can be conduction, we can have convection and radiation taking place simultaneously. In this type of processes, we can have conduction, convection, and radiation taking place simultaneously. The key question is, suppose now when you want to calculate the rate of heat transfer, what heat transfer coefficient do you deal with? Is it the sum of the individual heat transfers associated with the individual processes, or is it some function or form of it? So the most logical and straightforward assumption will be that you can actually sum the heat transfer coefficient associated with the individual processes. Unfortunately, it doesn't give you an exact solution. Therefore, the overall heat transfer coefficient which we will call U in our case, can be considered as a sum or some mathematical form can be considered as a sum or some mathematical form incorporating the individual transfer coefficients. So in a nutshell, what are we saying? That the overall transfer coefficient U can be a function of the transfer coefficient involved with the conduction, transfer coefficient of the convection, transfer coefficient of radiation. So that it has a functional form. That overall transfer coefficient will have the components, will have the overall, will be related to the overall, to the individual heat transfer coefficient for those particular processes. Now, let us look at a case in a heat exchanger. Let us look at a case in a heat exchanger. What's a heat exchanger? A heat exchanger is a system where we have two fluids exchanging heat, or the heat transfer between two fluids separated by a solid wall. In a heat exchanger, we have heat transfer between two fluids separated by a solid wall. Separated by a solid wall. Now, let us look at some forms of heat exchangers. We can have a parallel heat exchanger, parallel flow heat exchanger. And in a parallel flow heat exchanger, what are we dealing with? In a parallel flow heat exchanger, what are we dealing with? Let us draw a schematic of it. Here's our parallel flow heat exchanger. Parallel flow heat exchanger. let's have the flow is parallel. You just mark that. The flow is parallel. So if you plot the actual temperature and the heat exchange area, this exchange area, this is actual temperature. Then, what are we having? Those two fluids, remember, one is at a higher temperature, another is at a lower temperature. Why are we saying so? Remember that heat transfer occurs as a result of a temperature differential. So if the temperatures are the same, there's thermoequilibrium, there will be no heat transfer. So one of the fluids must be at a lower temperature, the other one at a higher temperature. So let us say that one is at a higher temperature, and the other one is at the lower temperature. This is for parallel flow. Parallel flow. And let us consider some elemental area, which we call dA. Elemental area dA. Now, to calculate the rate of heat transfer means that we must get a mean temperature for the two fluids. For the two fluids where we have the heat transfer taking place. So, here, the initial difference T1, T2, the mean temperature, the outlet. So this is temperature T1, temperature T2. And so, we observe that as the heat exchange area increases, the temperature of the fluid, which was initially at that temperature, decreases, while the temperature of the fluid, which was at the lower temperature, increases with the heat exchange area. That is the temperature of the fluid initially at higher temperature decreases as the heat exchange area increases. Similarly, are we saying the temperature of the fluid initially at lower temperature increases with heat exchange area. That is the case of a parallel flow. The case of a parallel flow heat exchanger. We have a counterflow heat exchanger. We have a counterflow heat exchanger where the two fluids are moving in opposite directions. Counterflow heat exchanger. Heat exchanger. Again, we have them moving in opposite directions. So we have the heat exchange area, and you have the temperature, the actual temperature. So again, in this particular case, if we take some elemental area just like we did, dA, temperature difference, sure. T1, that is temperature T2, T1, That's dt2, just like we saw with the parallel flow case. The T mean. So the terms are just the same. So what is the difference here? You notice that the fluid at the higher temperature, as it flows, the temperature drops, it cools. The temperature drops with the heat exchange area. And now also the temperature of the fluid, which was at the lower temperature, decreases with the heat exchange area. Remember, in the case of the parallel flow heat exchanger, the temperature of the fluid, which was at the lower temperature, was increasing with the heat exchange area. Now, for us to compute the rate of heat transfer, remember, we need to know the mean temperature that is between those two fluids, which is what we have there, delta Tm. So, to compute the rate of heat transfer, that will be very simple. We have dq will be u, the A to T1 minus T2, where u is the overall heat coefficient, dA is the elemental area, that is the surface area. The elemental area, that's the surface area between of exchange. And we have T1 and T2. Those are the temperatures for the fluid at the higher temperature and that at the lower temperature. And so, if there's no heat transferred to the surroundings, very important to note that. Similarly, if no heat is transferred to the surroundings, what does that mean? Then it means that Q will be minus M1 CP1 the T1. What is M? M is the mass flow rate of fluid which is at a higher temperature, which we are designating with the subscript 1. That is the specific heat, and that's that temperature change which we illustrated in the schematic or the diagram. And that must be equal to M2 T2. This is, of course, the subscript 2 represents those properties for the fluid at the lower temperature. That's very important for us to note. And so, dt1 is simply Q minus Q over M1 CP1. And dt2 is simply Q over M2 CP2. So now our life is easy. Our life has been made easy now, so we can quickly get expressions related to these flows. One of the things is, you know that d of delta T is d of T1 minus T2, that is dT1 minus T2. And so, what is that? D of delta T. Therefore, if we put in these values, we plug in those values, then clearly we see that is minus Q over M1 CP1 minus Q over M2 CP2. So this basically is D delta T will therefore be minus Q M1 CP1 plus Q M2 CP2. And this expression is very simple. It's very, very simple. In fact, you can pull out the Q so that it's not cumbersome, so that we have 1 over M1 CP1 plus 1 over M2 CP2. And even for the counterflow, it's very simple. Because in the case of counterflow, in the case of counterflow, for counterflow, in the case of counterflow, in the heat exchanger where we have the counterflow, the situation is Q now will be minus M1 CP1 dt1, and that must be equal to minus M2 CP2 dt2. Remember, we said that in the case of the counterflow, as the fluid which was at their temperature flows, as the heat exchanger increases, its temperature drops, it cools. And similarly, we saw that for the fluid at the lower temperature, in the case of the counterflow, the temperature drops with the heat exchange area. And that is why we have that minus sign, that particular point. And then again, now the same process is applied there, and you have the expression for the counterflow. Let's stop at that point. We'll pick up next time.